Alright, hey SPH3U, coming at you from the whiteboard view today because we're going to start with a demo. So today's topics are, there's a physical intro to calculating heat, and then we're going to talk about heating and cooling curves specifically for water. We're going to get into latent heat, and then specific heat, and then we're going to do a couple of practice problems if we have the time. If not, we'll just do that during the live class session on Zoom. So without further ado, we're going to hop into the live demo here. So what I've got set up is I've got two styrofoam cups, and just for posterity's sake, let's grab a mass on these styrofoam cups. This one is 3 grams. This one is 2 grams. It's not going to matter much. We're going to put like 100 grams of water in each of these, so that's not going to matter too much. Styrofoam is great because lots of air pockets, lots of insulation. It's white, so it reflects infrared rays. It's got this little rim. I don't know if you can see that. Oh, there. This little rim there. So that when it's sitting on a surface, it's not, the whole flat bottom isn't touching to conduct. It's only the rim that sits there to conduct. So there's a good amount of thermal insulation. Also got some thermometers. These are little barbecue thermometers, but they work pretty well. They give me to the degree, and if I hold it in my hand, you'll actually see it warm up because it's getting my body temperature by conduction. So I've got those. We're going to fill these up with water, and then later we're going to use vegetable oil to try it out. So I'm going to set that up and pause, and then when I unpause, we'll get that experiment going. Alright, and we're back. Now I've got them pretty close. This one is 150 grams, 153 grams. This one is 150, so they're pretty close to each other. Let's grab the temperature. Right, take this away. We can grab the temperature. This one is, I don't know if you can see it, maybe. Well, that's hard to see. Hang on, let me get rid of my learning goals. And we'll put up the current topic. Let's show that off. This one, can you kind of see it there? 19.0 degrees Celsius, about 19 degrees Celsius. This one, (47 degrees Celsius). So we've got equal masses. This one is 19 degrees Celsius. This one is 46.9 degrees Celsius right now, and they're both 150 grams-ish. They're very similar masses. So the question becomes, what happens if I mix them? If I pour one into the other? What is the, 46.9, what is the final temperature going to be? This is actually going down. So what I'm going to do is I'm going to wait for it to hit 46, because it's currently losing thermal energy to the air. It's at 46.5 right now. And then I'm going to pour the one into the other. So what do you guys think? Take a minute to calculate it. You might think it'll go directly between the two, right? There's a spread of from 19 to 46. You know, whatever's right in the middle there is probably going to be your answer. Well, let's try it out. I'm going to pour the hot one into the cold one, and we'll watch. We'll watch the temperature go, stir it around a little bit, and we'll show that off. 33.2 degrees Celsius is what I'm getting. 33.2, 33.1. So let's see if that matches our prediction. We got 33.2 degrees Celsius. Well, let's put that up here, 33.2 degrees Celsius. Is that right in the middle? Well, let's see. From 33 to 46 is 13 degrees. From 19 to 33 is 14 degrees Celsius. I'd say that's pretty close. So yeah, if that's what you predicted, you're correct. Well, let's set up the next one. Okay, we're ready with the next one. Let's see the masses. This is the cold one, 92 grams. So 92 grams on the side. Here's the hot one, 200 grams, 201 grams. And we'll get that out of the way. Let's get our temperatures. Hot one is at 44.5 degrees Celsius. And the cold one Twenty-two point six degrees Celsius. Now last time it was right in the middle, right? So this would suggest maybe it's going to be at 33. What do you guys think? Take a minute to form a hypothesis, maybe pause the YouTube video, but I'm going to go ahead and do it. So here we go. That's going to go in there. Pour it in there. Stir it around a little bit. And thirty-seven point five degrees Celsius. So not in the middle, right? More on this side of the line. Why would that possibly happen? Could it have something to do with the fact that we had more mass? Yeah, obviously it has something to do with the fact that we have more mass. Remember we said that total thermal energy is mass and temperature together. So this one not only has more mass, it's also a higher temperature. When there's heat transfer, this one takes more energy to raise its temperature by 1 degree Celsius than this one, because there's more water there. There's more jiggly motion. And so the transfer is lopsided. This'll the final temperature is more towards this side than towards this side, not right in the middle like we had before. Okay, we got one more, and that is with the vegetable oil. So give me a sec. Okay, now I've got that one set up. The vegetable oil, 144 grams. The water, 144 grams, eh? Not bad. So both of them are 144 grams. Take away the scale. Let's get those temperatures. The water, fresh out of my my hot water tap, sitting at about 46 degrees. The water's at 46 degrees. The vegetable oil, fresh out of the vegetable oil bottle. Come on. Sometimes it takes a little bit of stirring. 21.5 degrees. 21.5 degrees. That took a little while. Maybe this thing lost some energy. Let's see. Oh, still at 46 degrees. Okay, we're good. Okay, so 46, 21.5. Same exact mass. Same exact mass. What do you guys think is going to happen? Is it going to be right in the middle again? Is it going to be more towards the vegetable oil? More towards the water? Let's find out. So, if it was right in the middle, what's the average between 46 and 21.5? 46 plus 21, 67.5. Divide by 2 is 34. Is right in the middle. So let's see where we land. Let's see where we land. (41.6 degrees). Right, final temperature 41.6 degrees, 41.5 degrees. Isn't that weird? I think that's really weird. It's not even close to the middle. It's way more on the water side of things. So we'll jump back to this experiment and the results of this experiment in a little while. I might not have actually mixed this enough. Come to think of it, water goes on the bottom and vegetable oil goes on the top. Maybe we have to do more mixing. Let's try more mixing. Really get that getting mixed. I can see some water up on top. All right, get that up here. So yeah, with a lot of mixing, we can get it to like 30, 37. So maybe a little bit less than I thought, but yeah, 37. Right, higher than we think. Sitting at 38 right now. So we'll talk about that. We'll talk about why it pushed towards the hot water rather than the vegetable oil during this unit. So I'll pause it so that I can kind of clean up here, and then we'll go over to the note. All right, and I'm back and I'm set up to do the note. So what we saw in that experiment over there was when we had an equal amount of hot and cold water, the temperature ended up right in the middle. When we had more hot water, the temperature ended up closer to the temperature of the hot water. When we had an equal amount of hot water and oil, even though the experiment was kind of weird because I couldn't get the water and oil to mix really well, it was more towards the water than the oil, even though we had the same mass of water and oil. So where does that take us? Well, one easy way to kind of get an intuition for this is to look at heating and cooling curves. So I'm going to show, sorry about that, I accidentally hit pause instead of taking this away. So I'm going to show you this video that I found from Mr. Grotsky Chemistry, who's going to show us a heating curve. This starts as ice and it's going to heat, and you'll see the temperature on a graph behind it here. So this is ice, and it's frozen to the temperature probe as it's getting heated. You can see the curve, a nice steady line. And then something weird happens. Watch the ice melt, watch what's happening to the temperature. And then it's going to start to boil, and watch what happens to the temperature again. So that's the heating and cooling curve. So going back the other way is going to be a cooling curve. You'll see a very similar curve, and what you can see is a very linear, like time versus temperature, a very linear line, which suggests to us that it takes the same amount of energy, the same amount of time on the hot plate to heat the ice 1 degree here as it does to heat the ice 1 degree here. But that when it's water, it takes a different amount of energy to heat it by 1 degree. So that's a heating and cooling curve, and that's what it tells us about thermal energy. I'm going to pause for a second and get a picture of that, and I'll put that on here. Okay, found a good picture. Here is a heating curve for water. So it starts in the negatives as ice, and it's heating up from -30 ice up to 0 degree ice, still staying solid. Then it melts. You saw that in the video. You saw that. Then it starts heating up again as water, and it vaporizes. And then if it's a gas and you let it keep going, it'll actually keep heating up the gas as well. The steam can get above 100 degrees Celsius. And the lines have different slopes. The lines have different slopes here. This one has a steeper slope than this one, meaning that it takes less time to heat the ice by 1 degree, and more time to heat the water by 1 degree. So that's what we're getting into for heating curves, right? Let's start with this, latent heat. Latent heat. The symbol for latent heat is L for latent. Latent means hidden. And I'm going to move my little guy down here. Current topic is latent heat. Current topic is latent heat. And a little keep in mind, up on top, a degree Celsius is the same as a Kelvin, the same division as a Kelvin. So going from 0 to 1 degree Celsius is the same as going from 273 to 274 Kelvin. So latent heat. Latent means hidden. That's what the word latent means in Latin. It means hidden heat. What we mean by hidden is that you can't see a change in temperature during a latent heat transition, right? Water stays at 0 as it's freezing or melting, and it stays at 100 at air pressure, at standard air pressure, when it's being boiled, when it's being vaporized. So you don't see a change in temperature. That's why we call it hidden heat or latent heat. It's the energy of a change of state. It's very important that it doesn't change temperature during this, and so that's why we have it. I start with this because it's an easier one to understand. So here, for example, you've got the latent heat of fusion and the latent heat of vaporization. Vaporization, easy enough to explain, turning into a vapor, but it's also going back the other way. So it takes energy to turn a liquid into a gas. Turning a gas back into a liquid releases energy. And here's the latent heats of fusion and of vaporization. Fusion is the solid-liquid transition. So from liquid to solid, you're fusing it into a solid. From solid back to liquid, you are melting it, but that's still using the latent heat of fusion. So there's only 2 latent heats to remember. You don't need to remember one for boiling, one for condensing, one for melting, one for freezing, because the same transition has the same energy process. Remember, first law of thermodynamics is that the energy can't be created or destroyed. If you could gain more energy one way than going the other way, you'd have infinite energy if you took advantage of it correctly, which doesn't happen. So yeah, there's no change in temperature, and there's an equation here. We have our first equation, Q. Okay, Q is heat. Q stands for heat. I know, I'm sorry. Why isn't it H? It's because H stands for enthalpy. Okay, why isn't that E? Well, E is energy. Is the latent heat times the mass, right? Heat is latent heat times mass. Heat equals latent heat times mass. And it's just mass, right? Notice that this is joules per kilogram up here, joules per kilogram. Yeah. So here's a kind of a sample question. How much energy would it take to turn 1 kilogram of water that's already at 100 degrees Celsius into 1 kilogram of steam at 100 degrees Celsius? If you remember in the video, it just stayed at constant temperature. But more water would have turned into steam. Slowly that water would boil away. How much energy would it take? Well, it's actually just right here in our table. Here's water, right? Water, we're looking at the heat of vaporization because we're vaporizing it. Water is here, 2.26 times 10 to the 6 joules. So 2.26 times 10 to the 6 joules. Joules of energy. 2.26 times 10 to the 6 joules of energy, or put another way, 2,260,000 joules of energy. If our kettle is 1,000 watts, that's 1,000 watts per second, 1,000 joules per second. So it would take, therefore, the kettle, assuming the kettle was 100% efficient, would take 2,260 seconds to boil 1 kilogram of water. So 2,260 seconds is a lot of seconds. Let me just pull up a phone to calculate that real quick. I really should just have a calculator out now since we're doing math stuff. But 2,260 divided by 60, 37 minutes, 38 minutes. About 38 minutes. So you might have experienced this if you've ever forgotten a boiling pot of water on the stove. It doesn't take a long time to get the water boiling, but once it's boiling, it slowly loses water over time. And if you forget it for like about 45 minutes, all of it'll be gone. And you might end up with a fire on your hands because now there's nothing to absorb that heat. It's all going to go into the pan instead of into the water that's in the pan. So there's a simple question that involves the latent heat of fusion, or latent heat of vaporization. So that's an energy change. And it's important to note that temperature is not changing, but energy, total energy is, because we're constantly adding energy to our system. Yeah. So if you're wondering why the snow outside is taking so long to melt, it's because for every kilogram of snow, so every 2 pounds of snow, it takes 300,000 joules of energy to melt 1 kilogram of snow. There's a lot of energy in the sun, but it still means it takes a while. Yeah. So yeah, that's latent heat. Let's talk about specific heat, which is more interesting. Specific heat capacity. Specific capacity. That is one of those really good physics terms. Specific heat capacity is the amount of energy it takes to warm a substance up by a certain amount of energy. So here, for example, liquid water. Liquid water takes 4.18 joules of energy to heat 1 gram of it by 1 degree Celsius. So 1 gram of water, 1 degree Celsius, 4 joules of energy. If you had 2 grams, it would take, 8.36, right? 8.36. If you had to do, instead of 2 grams, you had 1 gram, but it was 2 degrees Celsius, it would still take 8.36. It would take twice as much. If you look at solid water, which is ice, it's about half the heat capacity, half the specific heat. So it takes less energy to heat up a gram of ice by 1 degree Celsius than it takes to heat up a gram of water by 1 degree Celsius. And you see some other ones here, like different metals and stuff like that, and rocks. We tend to think of rocks as like being able to hold a lot of heat, but in terms of their weight, they're actually not that great at it. Water is far and away one of the best heat capacity substances. Yeah, so that's that. Now the equation, because now there's a change in temperature, because we're warming it up, right? We're warming it up. Now there's a change in temperature. We have to add a new term here, which is this delta T, and this is big T. So please note, big T is temperature, right? Big T is temperature, not time. Change in temperature. Very important. Sometimes we'll actually have temperature and time in the same equation, and you got to know which one's big T and which one's little t. Liquid water has a very high heat capacity. It's also everywhere. It's important to life. We're 70% water. It's very common to heat up and cool down water. So that's our definition of the calorie. A calorie of energy can heat 1 gram of water by 1 degree Celsius. And it turns out from experiment that is 4.184 joules. 4.184 joules of energy. And you can see that up here in this table. A food calorie is 1,000 calories. That's a kilocalorie, and it can heat 1 kilogram of water by 1 degree Celsius, so 1,000 grams. Or you could heat a gram of water by 1,000 degrees Celsius. You couldn't do that because you've only got from 0 to 100 to deal with. Or you can heat 500 grams of water by 2 degrees Celsius, or 50 grams of water by 20 degrees Celsius, whatever. That's a kilocalorie. Yeah, so there's the summary of the actual math involved, the formulas involved. We're going to do some practice problems because I find this makes a lot more sense once you start actually doing a practice problem. And one big thing is because there's a conservation of energy, the heat that went from one thing to the other is equally matched by the heat that was absorbed by the first. So whatever this lost, this must have gained. Whatever this gained, this must have lost. That's why I say Q1 equals negative Q2. If something gained temperature, something else must have lost temperature. So I'm going to pause again and we'll pull up a practice problem and then we're going to solve it together. Okay, so here's our practice problem, one of our practice problems. It says, how many joules of heat are required to raise the temperature of 550 grams of water from 12 degrees Celsius to 18 degrees Celsius? And my camera is trying to sneak over too far that way, so let me try to fix that there. There we go. So from 12 degrees Celsius to 18 degrees Celsius. Well, let's solve one. So we only have one equation here, right? EQ is the change in thermal energy, which is mass times the heat capacity times the change in temperature. So this is mass, this is the heat capacity, this is the change in temperature. Note, it's the change in temperature, change in temperature. So we can pull this out of our thing here. What's the mass? Well, we already know that, it's 550 grams. Right, mass is 550 grams. Heat capacity, it's water, right? It says that it's water right there. And we know from that heat capacity is 4.184 joules per gram degree Celsius. Some very smart people did some experiments and worked that out for us for water. Then the change in temperature. What is the change in temperature? Right, we have 12 and we have 18, but the change in temperature is it went from 12.0 degrees Celsius and it went to 18.0 degrees Celsius. So the delta T, right, the delta T, if this is T1 and this is T2, delta T is going to be plus 6.0 degrees Celsius, plus 6.0. So that's actually what we're going to put into our equation. So to solve it then, Q is going to be mass times C times delta T. That's 550 grams times C, 4.184 joules per gram degree Celsius, times 6 degrees Celsius, the change in the temperature, plus 6 degrees Celsius, which gives us, we need to get out a calculator and actually do that. So let's bring up the calculator. 550 times 4.184 times 6 is, I get 13,807. 13,807 joules. It's in joules because the grams will cancel the grams. Grams cancels grams. Degrees Celsius cancels degrees Celsius. And then sig digs. We have 2 sig digs from our 6. Sig digs, 2 sig digs is 14,000 joules, plus 14,000 joules. The plus tells you that energy has to go in instead of it losing energy, and that just comes from the fact that it gained temperature. So that's how you solve a simple heat capacity problem. We're going to go to another one that's going to require a rearrange of the formula. So I'm going to pause, get to that, and then we'll start up again. Okay, here's the next one. We're going to solve this one together. This one is asking, there's a 250 gram sample of water. So let's see what we've got. We got mass is 250 grams. Initial temperature, T initial, is 98.8 degrees Celsius. And it loses 7,500 joules of heat. And that means that Q here is negative 7,500 joules. Negative, because it's losing energy. Heat is the change in energy, it's losing energy. We're asked for the final temperature. So this is kind of a 2-stage problem. Our equation is mass times C times delta T. It can give us the change in temperature. We can find the change in temperature from this equation. We know the initial, so when we take the initial and we apply the change, we will be able to figure out the final temperature. So let's solve it. We need to isolate delta T. Right now it's multiplied by M and by C, so we can divide it by M and C together, which divides Q by M and C together. So those will cancel out, but these ones won't. So then our expression is delta T is Q over M times C. We don't have C, well, we do, because they say it's water. So water, you'll always get the specific heat capacity of water. It's 4.184 joules per gram degrees Celsius. It's kind of like the acceleration due to gravity on Earth that like everybody knows is 9.81. Everybody knows that water's is 4.184. So you will automatically get that one. And you'll get any heat capacities you need to know on tests and things like that. So let's solve it. Minus 7,500 joules, that's Q, that's the heat, over the mass, which is 250 grams, times C, 4.184 joules per gram degrees Celsius. I'm going to do that all together on my calculator, on my phone, and just show you the importance of brackets while we're at it. Excuse me. Come on, adjust to the screen. Adjust to the screen. There you go. So what I want to do is 7,500, and I want to divide it by, and then I'll open the bracket, and it's 250 times 4.184, and I'll close the bracket. Okay, and I get an answer, 7.17 degrees Celsius, 7.17. Minus 7.17 degrees Celsius, because it was a minus, and minus 750, so minus 7.17 degrees Celsius. If I didn't do the brackets, here's what my calculator would have done. Ready? It would have, come on, adjust, there we go. It would have taken 7,500, divided it by 250, right? That's 30. And then it would take that 30 and multiply it by 4.184. And I would have gotten that the water is going to lose 125 degrees. That's, yeah, not good. That's not what
That's water can't even lose 125 degrees. That would tell you that something went wrong. Yeah, so we're losing 7.17 degrees Celsius. Lose 7.17 degrees Celsius. So, but we're looking for final temperature. So to figure that out, it's, straightforward. 98.8 degrees Celsius is what we started with. 98.8 degrees Celsius is what we started with. Take away what we lost. 7.17 degrees Celsius is equal to, it's too late in the day, I don't want to do math, so 98.8 minus 7.17, 91.63 degrees Celsius. So the final temperature is calculated to be 91.63. We need to do sig digs. We have two significant digits here, two significant digits here, so we need two significant digits. That takes us to 92 degrees Celsius is what we can safely say this thing is going to go to. So that's two different heat transfer problems and how you solve them. You guys will have some practice problems from this worksheet that we can work on together during the live class session. And if you remember this guy with the oil, let's check its temperature just for fun. Now it's at 34. Right, now it's been sitting here for a while. It's at 34. But that means it lost heat to its environment. The reason that the water, even though it was the same mass, the water kind of kept more of its temperature than the oil did, like it was further towards the water, is that water has that high heat capacity. It takes more energy to change the water's temperature than it does to change the oil's temperature. And so instead of meeting in the middle, the water resists more than the oil. So the water goes slower and the oil goes faster, and they meet more on the water's side. So there's two heat capacity problems for you. One that requires a rearrange, one before that doesn't. And I'll see you guys in the live class. Thanks for paying attention, and I'm going to sign off. Bye.